Dear students, after studying this module, you shall be able to know what is a linear free energy relationship, learn about the Hammett equation, know substituent constant and reaction constant, learn the derivation and application of Hammett equation, and understand physical significance of substituent constant and reactant constant in a reaction. Now students, let us begin our discussion with linear free energy relationships, also abbreviated as LFER. Linear free energy relationships compare the effects that substituents have on a rate or equilibrium process to the effects on a standard rate or equilibrium. Linear free energy relationships are attempts to develop quantitative relationships between structure and activity. Now changes in structure produce a proportional change in delta G. This is necessary because minus delta G is equal to RT ln natural log K is equal to 2.303 RT log K. According to this relationship, this is free energy relationship. Now the logarithm of rate constant K according to transition state theory is proportional to standard free energy of activation, that is delta G, and the logarithm of the equilibrium constant is proportional to the change in the standard free energy of a reaction, that is delta G naught. Hence, if there is a linear relationship between two sets of logarithms of rate or equilibrium constant, this is equivalent to a linear relationship between standard free energy changes, that is correlation is a linear free energy relationship. Now rate constant, also known as K, is equal to Kt divided by H e raised to the power minus delta G divided by RT, and equilibrium constant capital K is equal to e raised to the power minus delta G naught divided by RT. Now the linear free energy relationship which describes the effects of polar factors, that is I and R, inductive and resonance, on reactivity in aromatic compounds is known as the Hammett equation. Consider a particular reaction between two substrates. We might carry out a series of reactions by varying one of the reactants slightly. For example, by examining substituents with range of electronegativities. We might expect that the reaction rate or the position of the equilibrium between reactants and products will change as we change the reactant in this way. The same series of changes in conditions affects a second reaction in exactly the same way as it has affected the first one. We say that there exists a linear free energy relationship between the two sets of effects. Such relationships can be useful in helping to elucidate the reaction mechanism and in predicting rates of equilibria. Since delta G and delta G with two stars are combinations of enthalpy and entropy terms, a linear free energy relationship between two reaction series can result from one of three circumstances. The first circumstance is delta H is constant and the delta S, that is the entropy terms, are proportional for the series. Second circumstance may be delta S is constant and delta H terms are proportional. Circumstance may be delta H and delta S are linearly related. Now among the most commonly observed characteristics of reactions are their rates and their equilibrium constants, if at all they are observable. In this respect, the influence of substituents on reactivity often provides information about a reaction mechanism and has been the subject of extensive study by scientists. For example, the acidity constants for some substituted benzoic acids range from 3.4 into 10 raised to power minus 5 for the para-methoxy compounds to 6.7 into 10 raised to power minus 3 for the ortho-nitro compounds. A similar but not identical increase in the rate of base catalyzed ester hydrolysis has been noted, with the para-nitro compound reacting over 10 raised to power 3, that is 1000 times faster than the para-methoxy compound. Now, let us come to the discussion of Hammett equation. The Hammett equation and its extended forms has been one of the most widely used means for the study and interpretation of organic reactions and their mechanisms. Ever since the Hammett equation was developed, there were several hundreds of redox, condensation, disproportionation, nucleophilic and electrophilic substitutions and addition reactions with meta and para substituted benzene derivatives in the literature, for which the Hammett reaction constants were reported. Hammett's success in treating the electronic effect of substituents on the rate and equilibria of organic reactions led the scientist Taft to apply the similar principles to steric, inductive and resonance effects. Now, the Hammett equation correlates rates of reactions and equilibria for many reactions of compounds containing substituted phenyl groups. It was noted in the 1933 that there is a linear relationship between the acid strengths of substituted benzoic acids and the rates of many other chemical reactions. For example, the rates of hydrolysis of substituted ethyl benzoates. Now, Hammett plotted log K for hydrolysis of esters against log K for ionization of the acids, and a straight line was obtained henceforth. The reaction for basic hydrolysis of ester is as follows and is shown in the equation. Ionization reaction on the other hand of para and meta substituted benzoic acids as the standard equilibrium is as follows and is shown here. The correlation is illustrated graphically in figure, as you can clearly see, which shows log K over K naught, where K naught is the rate constant for hydrolysis of ethyl benzoate and K is the rate constant for the substituted esters plotted against log capital K by capital K naught, where capital K's are the corresponding acid dissociation constants. You can see that this is a plot showing correlation between dissociation constant of benzoic acid and rate of basic hydrolysis of ethyl benzoate with various substituents at para, meta and ortho positions. Now, a plot of log K, by K similarly I mean the small k as we were discussing, for base catalyzed hydrolysis of a group of ethyl esters against log of capital K for ionization in water of the corresponding carboxylic acids shows straight line relationship. The para and metabenzoic acid derivatives lie in a straight line, but the ortho derivatives lie off the straight line. The aliphatic derivatives lie to the other side of the line. It is immediately apparent that the rates and equilibria of the meta and para substituted compounds correlate well, but the ortho substituted compounds do not. This is not entirely unexpected, since the ortho substituents lie close to the reaction site and each may interact with different intermediates or the transition states in many different ways. The ortho substituent leads to crowding in the transition state, leading to low formation of the tetrahedral intermediate. Now, let us come to some mathematical equations. The equilibrium constant capital K and rate constant small k are related to free energy changes according to the equations. Now, log of capital K is equal to minus delta G naught divided by 2.303 RT, whereas log K or the small k as we depicted is equal to minus delta G star marked divided by 2.303 RT plus log K dash T over H, where K dash is the Boltzmann constant and the H is the Planck's constant. The linear correlation therefore indicates that the change in delta G star on introduction of a series of substituents is directly proportional to the change in the delta G of ionization that is caused by the same series of substituents on benzoic acid. The correlations arising from such direct proportionality in free energy changes are called linear free energy relationships. Derivation of the Hammett equation. Now let us try to derive the Hammett equation. The general equation for straight line, as you know students, is y is equal to mx plus c. From the plot showing correlation between dissociation constant of benzoic acid and rate of basic hydrolysis of ethyl benzoate, we henceforth obtain the equation log Kx is equal to rho log Kh plus C, where rho is the slope of the straight line, x represents meta or para substitution. For unsubstituted analogues where x is equal to the hydrogen atom, therefore log Kh is equal to rho log Kh plus C. From the equations 5 and 6, log Kx minus log Kh is equal to rho of log Kx minus log Kh. That is equation. Now coming on to equation, this becomes log Kx upon Kh is equal to rho of log Kx upon Kh. Now if we say log Kx upon Kh, that is equal to the small k, whereas the ones associated with rho is the capital K. Now as you can see, it is clear from the equations that we are showing you. Now log Kx upon Kh is equal to rho sigma x. Now this equation is called the Hammett equation, where sigma x is equal to log of capital Kx by capital Kh, that is again because it is a linear free energy relationship, it is equal to delta G naught divided by minus 2.303 RT or minus delta G naught divided by 2.303 RT. The quantity log Kx by Kh is equal to sigma x. Here sigma x is called the substituent constant and rho is the reaction constant, and it is the slope of the line, that is a straight line, which the general equation is y is equal to mx plus c. So m is equal to rho over here. Now keep a look at the table which shows the Hammett substituent constants and for the meta and the para substituents in the various benzoic acids. As you can see, there are variable values. A typical Hammett plot, here you can see it is a plot where the y axis is log k and the x axis is the sigma, and you can see as the sigma is less positive, the rho becomes negative, and as it becomes more positive, the rho also becomes more positive. That is, when rho is negative, electrons flow away from the aromatic ring in the rate determining step, whereas when the rho is positive, electrons flow away from the aromatic ring in the rate determining step. Now let us consider the conclusions from the Hammett plot shown here. A straight line plot obtained indicates that the free energy relation of the reaction is valid. The slope of the line is the rho of the reaction, that is a quantity, the slope of the straight line. A positive value of rho indicates that the reaction responds to the substituent effects as in benzoic acid, that is electron withdrawing groups increase dissociation and donating groups decrease the dissociation. If rho is greater than 1, then reaction is more sensitive to the effects than in benzoic acid. For benzoic acid, if we take the rho as 1, if the value of rho is between 0 and 1, then the effect is as in benzoic acid but lower because the value is less than 1. A negative value of rho indicates that the influence of the substituent is opposite to that of benzoic acid. That is, electron withdrawing groups decrease dissociation, and again electron donating groups, they increase the dissociation. If the value of rho is very small, it indicates that the reaction may involve radical intermediate or transition states. If the slope of the line changes abruptly, it is an indication in the change of mechanism as the substituents also change. Now let us take in deep discussion the substituent constant, that is sigma x. When the part of the molecule that we vary is a discrete atom or a molecular fragment, we call it a substituent. Now let us consider the substituent effects. Substituent effects are the changes in the reaction or property in an unchanged part of the molecule resulting from substituent variation. Effects of substituents on known reactions or properties of molecules tell us about steric and electronic characteristics of substituents. We can then use these substituents to influence chemical reactions and properties in predictable ways. Alternatively, we can use substituent effects to understand chemical reactions with unknown mechanisms or features. Now, considering the quantity log Kx upon Kh is equal to sigma x, here sigma x is called substituent constant. Its value remains constant for a specific position, that is meta or para, irrespective of the nature of that particular reaction in which a benzene derivative carrying this substituent is involved. In the Hammett equation, students, that is log small kx upon kh is equal to rho sigma x, by knowing the value of kx and kh, the value of sigma x can obviously be calculated. Now let us come to the next topic, that is the physical significance of sigma x. Substituent constant is independent of the nature of reaction and is a quantitative measure of the polar effects in any reaction of a given meta or para substituent relative to hydrogen. That is, it represents the electron withdrawing or attracting or electron repelling or releasing power of a particular substituent group. The more positive sigma is, more electron withdrawing is the substituent, that is minus I or minus R effect, and the more negative sigma is, the more electron releasing, that is plus I, this is plus inductive or plus resonance effect of the substituent is. It should be noted, students, that since electron withdrawal or release is referred to hydrogen as standard, the sigma value for hydrogen is 0. The change in sign of sigma m minus x from negative to positive parallels the change in direction of electron donating group to electron withdrawing group of the inductive effect exerted by these substituents. Now electron donating groups such as trimethyl carbon at the meta position and M-methyl have small negative value of sigma m minus x. H has a 0 value of sigma m minus x. Electron withdrawing substituents at the meta position have a positive value of sigma m minus x. The substituents may also exert a field effect operating through the medium, but will act in the same direction as the inductive effect. Thus, sigma m minus x represents both in direction and magnitude a measure of the total polar effect exerted by the substituent X on the reaction center. Polar effects are greater in para position than in the meta, and the halogens are certainly an exception. Sigma values may be related to the orienting power of the group. Substituents whose sigma values are more negative for the para than for the meta position, example amine, methyl, increase the general reactivity of the ring for electrophilic reagents and hence are ortho and para directing. On the other hand, substituents whose sigma values are more positive for the para than for the meta positions, for example the COMe group, that is the O-methyl group, the nitro group, lower the general reactivity of the ring for electrophilic reagents and hence the meta orienting. The positive sigma values of the halogens indicate a lowering of the general reactivity of the ring, but in these cases the para values are more negative than the meta values and hence the halogens are ortho and para directing. Reaction constant rho. Reaction constant rho is a measure of susceptibility to influence the substituent group on the rate constant or equilibrium constant of a particular organic reaction involving a family of related substrates. The empirical rho sigma equation, defined as the Hammett equation for the effect of ring substituents in meta and para positions of aromatic side chain reactions, is of the general form log Kx by Kh is equal to rho sigma x, in which the sigma x is a constant characteristic of the substituent X and of its position in the reactant molecule. Now, after calculating the value of sigma x, it is possible to calculate the value of reaction constant rho. Let us discuss the physical significance of reaction constant rho. Reactions with a positive rho value are accelerated, or the equilibrium constants of analogous equilibria are increased by substituents with positive sigma constants. Since the sign of sigma was defined so that substituents with a positive sigma increase the acidity of benzoic acid, such substituents are generally described as attracting electrons away from the aromatic ring. It follows that reactions with a positive rho value are considered to involve a transition state or a reaction product, so that the difference in energy between the state and the reactants is decreased by a reduction in electron density at the reactive site of the substrate. Reaction constant rho is dependent on the nature of the reaction and on the conditions. It is a measure of the sensitivity of a given reaction series to the polar effects of the ring substituents, that is, to the changes in the sigma value of the substrate. Now, you can see here the meaning of different Hammett rho values and their discussion. If sigma is positive, that is for the electron withdrawing groups, then K is greater than K naught, or for capital K is greater than K naught. If rho is positive, thus for reactions in which rates or equilibria are facilitated by electron withdrawing groups, then rho is positive, or alternatively reactions for which rho is positive are aided by electron withdrawing groups. If sigma is negative, then K is less than K naught, or to say capital K is less than capital K naught. If rho is negative, thus for reaction in which rates or equilibria are hindered by electron withdrawing groups, rho becomes negative, or let us say alternatively reactions for which rho is negative are hindered by electron withdrawing groups. By similar arguments, it can be shown that reactions with a positive rho are hindered by electron releasing groups where sigma is negative, and those with a negative rho are facilitated. Also, a positive rho value means more electrons in the transition state than in the starting material, and a negative rho means fewer electrons in the transition state than in the starting material. Now, for a given positive sigma value in different reactions, the more positive rho is more K, or the capital K, greater than K naught, or the capital K naught. That is, the greater is the effect of the substituents on that reaction, or let us put it alternatively, the more sensitive is that reaction to polar effects. Similarly, the more negative rho is, the more is the K, or the capital K, and smaller is the K naught, or the capital K naught. You can clearly see the gradient of this best fit line shows how sensitive the reaction is to the substituent effects in comparison with the ionization of benzoic acids. Now, let us consider the comparison between the substituent constant sigma x and the reaction constant rho. Sigma is a measurement of capacity to perturb electronic environment, and first values were described by Hammett, and it is referenced to hydrogen substituents and the value for hydrogen is 0. Over the next 20 years, values averaged over several series of reactions to give good correlations for all values. Whereas in comparison, let us talk about rho. Rho is measurement of sensitivity of a reaction to electronic perturbation, and it is individual for each reaction. It is reference to equilibrium of benzoic acids in water at 25 degrees Celsius and the value is 1. Magnitude and sign can be diagnostic of a reaction mechanism. Now I hope you can appreciate the difference between sigma and rho over here. Now let us come and talk about the application of Hammett equation. First, we would like to discuss the calculation of rate constants. Experimentally, one determines capital Kx for various substituents and plots log Kx by Kh or log Kx versus sigma. The slope of that line is rho, hence reaction constant can be easily calculated. Now, as you can see, here we have described, now in this table you can see for various types of reactions the various rho values are given. And now we will discuss the second application, that is the use of Hammett p values or the rho values to discover reaction mechanisms. Consider these two reactions which are very similar, a reaction with bromine and one with PHSCl, that is the thiochloride. With no further information given, we might be tempted that both go by the same reaction mechanism. However, the Hammett rho values for the two reactions are rather different and might make you change your point of view for the mechanism of the reaction. The rho value for bromination is definitely in the large range and can only mean that a positive charge is formed, that is delocalized around the benzene ring. Instead of forming a brominium ion, the bromine prefers to form a benzylic cation instead. Now you can see these in the figures that we have given. Now rho value of sulfinylation is quite moderate since no cation is formed around the ring, but electrons flow out of the ring and we suspect loss of conjugation. Now this fits well with the formation of three-membered intermediate. For example, experiments like this, from this we learn that PHSCl, which is involved in the sulfinylation, is much more likely than bromine to react stereospecifically with alkenes through a cyclic intermediate. Now third application is obtaining a complete picture of the transition state. The Hammett rho values are a good judge of studying a reaction taking place between a nucleophile and an electrophile. The Hammett plots from the variation of substituents on both reagents can give us details about the transition state and its nature. Now let us consider some deviations from the ideal Hammett equation. If in a given reaction series there is a deviation from the Hammett equation, there is a strong indication that this particular reaction is proceeding by a mechanism different than we expected, that is a mechanism for the rest of the series. Now a reaction occurs by the faster of the two possible mechanisms, but by the slower of the two possible steps, that is the rate determining step. When the only polar connection between a substituent group and a reaction center is an inductive effect, the Hammett equation holds good. When however, resonance is possible between the substituent group and the reaction center, this resonance affects the rate or the equilibrium position in addition to the inductive effect. Resonance effects of this kind are the one of the main causes of the failure of the ideal Hammett equation. Now let us summarize this module. Linear free energy relationships, that is LFER, compare the effects that substituents have on a rate or equilibrium process to the effects on a standard rate or equilibrium. The linear free energy relationship, which describes the effects of polar factors, that is inductive and resonance effect, on reactivity in aromatic compounds is called as Hammett equation. The Hammett equation correlates rates and equilibria for many reactions of compounds containing substituted phenyl groups. It was noted in the 1933 that there is a linear relationship between the acid strength of substituted benzoic acids and the rates of many other chemical reactions. For example, the rates of hydrolysis of substituted ethyl benzoates. Now, considering the equation, log Kx upon Kh is equal to rho sigma x is the final derived Hammett equation. Hammett plotted log K for hydrolysis of esters against log K for ionization of the acids. A straight line hence was obtained. Now, a plot of log K for base catalyzed hydrolysis of a group of esters against log of capital K for ionization in water of the corresponding carboxylic acids shows a straight line relationship for meta and para substituted derivatives. However, no straight line is obtained for ortho substituted compounds. Experimentally, one determines capital Kx for various substituents and plots log capital Kx upon Kh or log capital Kx versus sigma. The slope of the line hence obtained is rho. Substituent effects are the changes on a reaction or property in the unchanged part of the molecule and resulting from a substituent variation. The quantity capital Kx upon Kh log is equal to sigma x, where sigma x is called the substituent constant. Substituent constant is independent of the nature of the reaction and is a quantitative measure of the polar effects in any reaction of a given meta or para substituent relative to hydrogen. That is, it represents electron attracting or withdrawing or electron repelling or releasing power of a substituent group. Now, reaction constant rho is a measure of the susceptibility to the influence of substituent groups on the rate constant or equilibrium constant of a particular organic reaction involving a family of related substrates.